Hello and welcome to this AfterMaths episode of the Primary Maths Podcast, the show where we talk all things primary maths with me, John Cripwell.
And with me, Becky Brown.
Hello, Becky. How are you this week?
Hello, I'm very well, thank you. It's always a little bit strange working in half term when you're so used to having half terms off, but it's been a quiet one. It's been nice to have the family around, although I'll be glad to get back into a routine next week. How's your week been?
Yeah, no, it's been okay. I hope everybody listening has had a lovely week. If you've had half term, I hope it's been a good one and that you are maybe not sufficiently rested. Maybe that's asking a lot, but feel like you've had a little bit of a break from school.
Yeah, I always loved February half term. I felt like October half term was always desperately needed because the first half term was a tough one. Christmas is very busy, and it got to February and it's like, oh, actually, I have quite a chilled week this week. So hopefully that's what the listeners have done this week.
Yeah, absolutely. The thing is, there's just not that much to do at half term in February, whether you've got children or not. I think it's I don't know anybody that's gone away abroad this half term. I think you have to go quite a long way to find some sun at this time of year, don't you? But if you have, then please do feel free to rub our noses in it and send us your exploits of where you managed to get to this February half term, somewhere sunny, hopefully. So we are not going to talk too much about school on today's episode because it is half term. I just wanted to share a little bit of research that I've been doing into a very specific part of maths that we teach in upper key stage 2, I suppose, although children begin to notice it maybe a little bit earlier. And if I said the numbers to you, Becky, 2, 3, 5, 7, 11, 13, what would you be thinking at that point other than just John's rubbish at his times tables?
I would be thinking you would be listing some prime numbers for me, John.
I would indeed, yes. Prime numbers. We are going to do a little bit of a deep dive into prime numbers because I did ask last week on last week's AfterMaths episode for people to get in touch if they would like to know a little bit more about a particular subject, and prime numbers was one of those that came up. And I thought, yeah, I've always found them interesting. I found them interesting to teach and to think about a little bit. But I also sort of questioned why. Other than they are a little bit interesting, why are they important? And it turns out, Becky, you probably already know this, but it turns out they are very important indeed. So, I thought we could take a little bit of a circuitous route through the history of prime numbers and why they are still important today. And when I mentioned this to you earlier, you did say that you did have a little bit of knowledge of prime numbers for a very particular reason.
I do. So my husband, who is a secondary maths teacher and has a master's in maths, did his dissertation on large prime numbers. So I won't go so far as to say I read it, but I have looked a little bit deeper into prime numbers in the past, and a favourite of mine to teach as well, actually, John. So really excited about this conversation today.
He didn't read his magnus opus, his life's work. You just left that. No. Did you know him when he was doing this? Or
yes.
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 And you were like, I'm sure it's lovely. I'm sure it's great. Well done. Yeah, it's not for me.
I mean, I think if it was lying around now, I probably would have a read. I think it's in the loft. I probably would have a read of it. But yeah, I mean, he summarised it for me. That was enough.
Yeah, I mean, you had the human version of it there, didn't you? I'm sure you discussed it late into the night on many occasions. Large prime numbers, and I can't think of anything more romantic, really, Becky.
No.
Actually. Yeah, how beautiful. Okay, so when I was looking into this a little bit, I sort of, I guess I thought, what do we teach? And one of the things that we first teach is that prime numbers are a multiplicative relationship, aren't they? And it's around finding numbers that have exactly two factors, one and itself, which is why 2 is an interesting prime number, isn't it? Because it's the one that lots of children and some adults forget about because obviously it's the only prime number that is even because it only has two factors. So there's only it's only in the 1 times table and the 2 times table. And that's what makes it prime. It doesn't feature in any other times table. But of course, every other even number is not a prime number. We call those composite numbers, don't we? If they're not prime, then they are composite. And every other even number has to be a composite number because it's got the 2 as one of its factors, as well as itself, and 1. So every even number has got at least 3 factors, which is what makes 2 interesting. So we know that every other prime number is odd, but they don't really follow a pattern, which is frustrating from a maths point of view.
Yes.
Because maths,
Yeah.
Becky, it's all about order and, patterns and reasoning. And, if you pretty much every times table that you look at, if you plot it onto a 100 square or onto a multiplication grid, you start to notice patterns in it, don't you? You can see, where the next one is likely to be. But that doesn't work with prime numbers. They're a little bit annoying.
No, and it's very tempting. I mean, when you were reading them out earlier, you always have to remind yourself not to say, for example, 9, because it
9,
feels like
yeah,
it's going to be 1.
yeah,
Because up to that point, you've listed odd numbers apart from 1, obviously, which is also special because it doesn't fit into either camp. But
yeah.
yeah, you have to sort of
Tell me
remind
why
yourself.
1 is special, Becky. Why isn't
So
1 a prime
1
number?
only has 1 factor, and I think this is where we can complicate it, can't we? Because I've heard people often define them as, prime number is a number that has a factor of 1 and itself.
It
And
can
if
be
you think
divided by
about it
1
like
and
that,
itself. Yeah,
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 you sort of think, actually, using that definition, you could be persuaded to think that 1 was 1. But when you
yeah,
simplify it to it's a number with 2 factors, that's enough, isn't it? And you think, actually, 1 only has 1 factor and therefore isn't
yeah.
prime or
Exactly 2
composite.
factors. It's got to have 2
Yeah,
factors,
exactly
no
2.
more, no
Yeah.
less. Yeah. Yeah, so 1's interesting because 1 seems to fit the bill, but it isn't 1. And 2 is interesting because it books the trend. But then all the others kind of book the trend as well, because as you say, you start going up in what seems like a pattern, 3, 5, 7. Oh no, we skip 9 because obviously that's in the 3 times table, as well as the 9 times table and the 1 times table. And then we go on to 11 and then 13, and we seem to be back on track, don't we? And then suddenly 15 pops up and you think, no. So it's an interesting one. It challenges your thinking a little bit, doesn't it? But prime numbers are more than just the sum of their parts, if you like. So it is true that they only have 2 factors and must only have 2 factors. But Becky, have you ever heard of? I feel like I need to put a voiceover on this, like a deep bass voice. But the fundamental theorem of arithmetic.
Yes, but but only
Only because
through
you're so
you
cool
looking
and
at
you spend
price.
spend your
Yes.
evenings discussing
Talking
prime
about
numbers.
prime numbers. Yeah.
Yeah. So the fundamental theorem of arithmetic, it's not in the Key Stage 2 curriculum, funnily enough. However, I do think it's, something that we sort of touch upon, but we just don't give it a name. It essentially says that every integer that is greater than 1, so every whole number that is greater than 1, is either a prime number itself or can be represented as a unique product of prime numbers. So that whole idea of sort of prime factors and things. And therefore, prime numbers are kind of the building blocks of all integers. All integers can be reduced down to a pair of prime numbers, which is interesting, isn't it? They're
Yeah.
sort of like the atoms. So 12, for instance, isn't just 12. We can make 12 by multiplying 2, 3, and 3 again. So you've got those 2 prime numbers, 2 and 3, which can make 12. And 100 is 2 times 2 times 5 times 5. So we've got those prime numbers that kind of make everything else. And that's kind of why they're interesting. But who first spotted prime numbers, Becky? Which group of people in history do you think, as far as we're aware? I mean,
Oh,
records are patchy, aren't they? So maybe somebody before this spotted them, but as far as we're
okay.
aware.
I'm going to guess, and it's just a guess, The ancient Greeks.
Oh,
Oh, no.
of course, it's
Is
those
it?
lot again. It is,
Oh,
yeah, it's the ancient Greeks, yeah. So specifically, Euclid. So you've heard of Euclid, I would imagine Euclid mathematics and things, famous historical mathematician. We don't know much about the person, the man Euclid, because he lived over 2,000 years ago. Shortly before, shortly after, sorry, several of Plato's followers. So around 300 BC, something like that. So 2,300 years ago, something like that. And basically, what he's most famous for is creating a textbook. He kind of took all the other great mathematicians that had come before him, all of their ideas, and wrote them into this huge textbook, 13 books in this series of textbooks called The Elements. And that was kind of his great life's work. He got stuff in there from Hippocrates and Thales, Thales, yeah, and Plato and Aristotle, and sort of put all of those together into this big textbook, that and elements of which it's called Elements, exist and survive to this day. So it's kind of the one of the original maths textbooks really that pulled everything together. But he also had his own theory within there, and what he proved in that textbook is that there are an infinite number of prime numbers, which is bonkers when you think about it, because we know as we go through, even if you just did prime numbers up to 100, that you get fewer of them as you go, because obviously there are more numbers which could be factors of those
yeah.
larger numbers. So to say that there's an infinite number is mind-boggling to me, really.
Yeah.
And
Infinity is frightening anyway, isn't it? I mean, I
well, it
try not
is,
to
yeah.
think about it too much.
Funnily enough, I was talking to my 8-year-old, she's now 8, 8-year-old daughter the other day, and she was saying, how can there be an infinite number of numbers? How can there be a number, there must be an end number. I was like, no, because you can, whatever number you say to me now, we can add one to it and get another number. Like there is no, it takes a little bit of getting your head around, doesn't it?
Yeah.
But it's fascinating. And maybe one day we'll talk about the infinite hotel. I don't know if you've come across that idea, but it's one of the ways of exploring infinity. And it's
Oh,
a really nice thought experiment, and one that I used to do with children at school as well. So that's a nice one for another week, but
oh
not
yeah.
for
Save
today,
that.
Becky.
No, one
Um,
exciting thing at a time.
Yeah. So Euclid, fascinating because he didn't have algebra, he didn't have modern notation, he certainly didn't have Google spreadsheets or any other sort of spreadsheet to help him with this. But he basically um, mathematically proved that there are an infinite number of prime numbers, and he did it in a way that is very nice and neat, that I don't necessarily understand, but that good mathematicians tell me does make sense. Essentially, he said if you think you found all of the primes, you multiply them together and then you add one, you've either created a new prime or something with a new prime factor. So yeah, I don't really understand that, Becky, but it sounds good, and I'm happy for him that he did that. But yeah, 2,300 years ago.
Wow.
So prime numbers were around before Euclid, but he was sort of the first one that we know that wrote about them and sort of talked about them and stuff. And then we fast forward just a little bit to a guy whose name I'm going to take a slight run up at, called I practiced this earlier, Becky, and now I'm feeling not enough. Eratosthenes. Eratosthenes?
Sounds good to me.
Yeah. Yeah, just obviously that's what it is. So this is not a guy that you want to compare yourself to if you are feeling in any way inadequate or like an underachiever, because he was kind of the original polymath, really. He was a philosopher, a scholar, a mathematician, a geographer, a poet, an astronomer, and a music theorist, of course.
Wow.
And then he went on to become the chief librarian at the Library of Alexandria, which was kind of one of the, repositories of all the world's knowledge, really, back in ancient days. So, yeah, he had a lot of strings to his bow. He lived into his 80s, which is remarkable for kind of, again, 2,000 years ago. He proved and calculated the Earth's circumference in 240 BCE. And he also was the first person to calculate the tilt as well of the Earth. And he did both those things remarkably accurately. The circumference he did with shadows. Have you heard this story before, Becky?
No, I don't think I have.
So he noticed that at noon on the summer solstice, as you do, where else would you be looking at noon on the summer solstice other than down a well? And he noticed that at noon on the summer solstice, the sun shone directly down a well in one city, but cast a shadow in another city slightly further north. And so using geometry and the distance between the cities, he was able to calculate the Earth's size to a ridiculous degree of accuracy, which is just bonkers. Yeah, and I'm obviously not doing, I do a podcast, but, there you go.
Still very much appreciated, but maybe not as groundbreaking.
No, maybe not. Well, hey, it's early days. It's early days.
Give it time.
However, he also invented the Sieve of Eratosthenes. Eratosthenes?
Now, I have heard of that. I don't know if that's how you pronounce it, but I have heard of that.
Of course that's how you pronounce it, Becky. Why are you doubting me? For anybody who wants to double check on the pronunciation of that, it's Eratosthenes. So essentially, this is where we get back to prime numbers. It's an efficient algorithm for finding all the prime numbers. So you know what it's like when you're in class, you're talking to children, and you're saying, is 24 a prime number? And they say, no, it can't be because it's even. So it's got, factors of 2, 24, and 1. Okay, so is 23 a prime number? And that takes a little bit more because you have to be really confident, don't you, of all your division facts in order to know whether 23 is a prime number or not. So one thing that you can do is use this particular sieve. So what you do is you create a list of integers from 2 to up to the number that you're trying to work out if you want to. And you start with the first prime number, which is 2. And if you've got 100 square, this works really nicely. You mark off all the multiples of 2 on the 100 square, so you can get rid of all of those. And then you do the same with 3, and you do the same with 4. And obviously you don't really have to do 4 because you've already done it with 2. So it's quite an efficient way of doing it. And you just need to do that up to the square root of the number that you're working at, really. And so it's a really nice, efficient way of finding small prime numbers. Doesn't work when you've got prime numbers with millions of digits quite as efficiently. You'd be there for a long while. Yeah. But it's more efficient than just trialing division facts for some people. So, yeah. So for example, if we were finding primes up to 10, we could list out 2, 3, 4, 5, 6, 7, 8, 9, 10, mark the multiples of 2, mark the multiples of 3, and then just having done that, you will have already found that the prime numbers are 2, 3, 5, and 7. So this is just circling back around to the idea that primes don't follow a neat pattern. We've already touched on this a little bit. We know that mathematicians, we hate randomness, don't we?
We do.
That's the whole point of maths, is that it sort of organizes things nicely for us. So we're going to skip forward to the mid 1800s now, Becky, as we're thinking about prime numbers. And we, at this point, enters Bernhard Riemann, who is a German mathematician. And this guy, honestly, go and have a look at him, see his portraits from the sort of mid 1800s. If you were to draw a Victorian-looking mathematician, you would essentially draw Bernhard Riemann. Okay, he's got a little bit of a comb over going on, formal Victorian sort of suit, beard, glasses, the works, and he only lived to be 39, but clearly in one of those days where people who were 39 looked a lot older than people who are 39 now, if you know what I mean. I'm not even sure when the portrait was taken, but yes, he looks like a Victorian mathematician. But he was trying to understand how these prime numbers are distributed, and he proposed the Riemann hypothesis, which is still unsolved. So he essentially said that there must be a pattern. There must be. but nobody yet has found one. But if you do, Becky, and this might be another way to spend the rest of your half term, if you can prove a pattern of how the prime numbers are distributed, then it is one of the Clay Mathematics Institute's Millennium Prize problems, and you will bag yourself $1 million if you could do that. So, worth getting
Wow.
a pen and paper out and just having a little look
Get
down at
started.
these.
Yeah.
Yeah, why not? Yeah, how difficult can it be?
Yeah. If nobody else has found it, maybe I could. Who knew?
Exactly, yeah. But, it's a nice thing to tell pupils in the class,
Yeah.
and one day, if you learn about these prime numbers, you might bag yourself $1 million by figuring out how they're distributed. So, why are prime numbers important then, Becky? Bring it up to the modern day. Can you think of a way in which prime numbers affect our day-to-day, a little bit maths of life here? Can you think of a way in which prime numbers are important?
Well, I mean, I can't think of one, but I do know that they are used in encryption, I think, aren't they?
They absolutely are. Yeah, yeah. You've been reading my private show notes again. I can see.
It's that
So
dissertation. It's the
yeah,
dissertation summary.
that'll be it. So essentially, prime numbers are the reason that secure encryption works. I didn't know much about this. I had a little look into modern cryptology. Cryptography, including RSA encryption. Now, I assumed that RSA stood for something like random semi-automatic encryption or something like that. But it's three mathematicians' names. So we've got Ron Revest, Adi Shamir, and Leonard Edelman. So Rivest, Shamir, and Edelman, RSA. And they created in 1977 RSA encryption, which is essentially the basis of most modern computing encryption technologies that we use now. Online banking, shopping, passwords, government communication. Every time you tap your card, basically, to pay for something, it will use some form of encryption that's based on this. And the way it works, and I've simplified this from my understanding, Becky. I
Good.
did have a look at some of the equations, and I didn't understand any of them. Maybe Pete Mattock would be better placed. I don't know, but there was a lot of letters and symbols, some of which I didn't understand. However, essentially, it's really it's really easy. If you've got a computer, it's easy to multiply two large prime numbers together, okay, and
Yeah.
find the product of two large prime numbers. But it's incredibly hard to go backwards from there. But of course, the product that you've made only has those two prime factors, those two large prime factors. There are no smaller prime factors than that because you've just multiplied two prime numbers together. So they sort of become the key to unlocking this encryption. So it's easy to create the sort of encryption number by multiplying two large prime numbers together, but it's really hard to undo that if you don't know what the two large prime
Yeah.
numbers were.
That makes
And when
sense.
we say
Okay.
large prime numbers, we're talking about prime numbers potentially with millions of digits. Not always, some of them are more simple than that, but there are some very large, as you will know, some very large prime numbers out there. Just another thing, I suppose, to explain to pupils in the class, prime numbers affect every day of our lives now. Any time that you're
Yeah.
communicating online, anywhere that you see that little padlock symbol on the website indicating that there's some sort of secure website, prime numbers will be involved in there somewhere. It's all there, Becky.
Yeah. See, there is a reason behind it all. Just have to
Exactly.
find it.
Yep, there is. Now, large prime numbers. The largest prime number isn't something that you're going to be able to write on a board. And I'm guessing maybe the reason your husband chose large prime numbers was because he could get up to his page count really easily just by including one of them.
Yes.
I mean, that would be great. You just copy it all out digit by digit. You pretty much got the size of a normal, what are they called?
Dissertation.
Thank you. Dear me. So the largest prime number has got millions of digits, the largest prime number that we know. Obviously, as Euclid proved, there are an infinite number of them. But many of the biggest known primes are Mersenne primes. named after Marin Mersenne, who is the last person that we're coming across today, Becky. But he was a 17th century monk. And clearly had a lot of time on his hands because he got very interested in prime numbers. One of those rabbit holes he can just fall down, I guess. But I just think it's really, and he found some really, really big prime numbers, proved these enormous prime numbers existed. I just love the fact that 400 years ago, we got this monk in a monastery working out these huge prime numbers that 400 years later kind of form the basis of secure computing systems.
Yeah.
He just couldn't possibly ever imagine that, could he?
No, I love that. It's a lovely narrative, isn't it, behind it?
Yeah, it's really nice. So just going back to the classroom, I like prime numbers because they're a really nice way to talk about number properties, I think. Help us spot patterns, reason about divisibility, explore proof. It's a really nice way to begin to explore proofs, I think. Talking about infinity, and we will come back to infinity because I like infinity, even though it scares me a little bit. And also, the thing that's nice about prime numbers, I think, Becky, is that it's not finished. Nobody has proved all the things about it. So we think about maths as being right or wrong all the time, but actually there's things that we still don't understand about it.
It's more
Still
to come.
mysteries. Yeah, still mysteries there. Still million-dollar problems to be solved.
We did have for a time, our computer was part of the great internet Mersenne Prime search,
Lovely.
which you can sign up for, and there's computers everywhere trying to find the next one. That is how the most recent one was found, I think, using that sort of virtual program. But yeah, I think, is it 41 million digits in the largest one? I think at last count, something like that.
Wow. Just the 41 million.
Yes.
I can remember pi to about 5 digits, so I've got a little way to go to remember the largest prime number. But pi is another nice thing, isn't it? I used to, when we were in year 6 and we started thinking about pi a little bit in circles and things, I used to find the pi to X number of million digits or whatever it was and put it up on the board and just scroll through for a minute for the children to see that, how
Goes on
long
forever.
this, and yet it's smaller than 3.5. Do you know what I mean? Like it's still a very small number, even though it has a ridiculous number of digits. I think it's a great way, as Joe was talking about on the podcast a couple of weeks ago, just those ways of unpicking misconceptions about numbers. This idea that this pi has got an infinite number of digits attached to it, but it's still a very small number. Just challenges that perception.
Pi is quite fascinating, isn't it? Just on its own, really, how it all works.
Yeah, what's your favourite flavour?
But cherry.
I was going to go cherry as well. You can't beat cherry pie with a dollop of ice cream or custard. I'm happy either way. Cream at a push.
Custard, I reckon, for me.
Yeah.
My favourite prime number, I just have to share this with you because
please.
I love it, is now I'll read it as a number first. I've written it down so I don't get confused over my quintillions and things. But you've got to try to imagine it, if you can, written down in digit form, is 12 quintillion, 345 quadrillion, 678 trillion, 910 billion, 987 million, 654,321.
I've got it. That is beautiful. That is really, really nice.
It's a prime number. Isn't that lovely? I love that.
Just in case anybody hasn't spotted the pattern there, because as you were reading it, it could be, if you're not listening intently, you might have missed it.
So in digit form, it's basically the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10, then back again 9, 8, 7, 6, 5, 4, 3, 2, 1.
That can't be a coincidence.
Beautiful.
That can't be a coincidence. I love that. I need to understand that, but I don't think I ever will. So there you go. There is our deep dive into prime numbers for you. Hopefully, what I really wanted from that, Becky, was just a couple of kind of takeaways that people could take back to class and just share with pupils, or if not, just for your own enjoyment, really. But all the way back to Euclid and before, and then up to RSA encryption in 1977. And back into our classrooms today. Prime numbers, fascinating stuff. So that is our half-term special for you. If you didn't enjoy it, well, then tough, it's over now. You've clearly listened to it at this point. But what you could do is suggest a different topic for us to investigate for Easter, because we'll have a couple of Easter specials coming up. So we'd love to hear what you would prefer to hear then instead. But I had a lovely time, Becky, so I'm not really worried.
Yeah, I did too. I love talking about that. I just find that beautiful. That sort of when those things just work together, and prime factorization. That's great.
Yeah.
And if I'm sure if you got with us this far, hopefully you did enjoy the episode. And
I'm
if you can
sure.
give
I'm
us
sure.
a quick
It's
like,
not just
that would
that
be great.
somebody's lost the remote or, can't find
Yes.
wearing gloves because it's cold, so it's really hard to press the stop button.
Stuck till the end.
Yeah. Yes, please do give us a like, give us a subscribe. We'd really appreciate it. Hundreds of other people already have, so join the club, please. We will, and that will mean that you won't miss our next episode, which is on Monday. We've got an international. No, it's not. It's on Tuesday. I apologise. We've got an international flavour next week, Becky, because I have been speaking to Kate Quain from the University of Adelaide in Australia. I won't do the accent. Did think about it. And we are talking about porridge words and basically mathematical thinking and the importance of recognizing attempts at using correct mathematical vocabulary. If you've been thinking at all about how important correct mathematical vocabulary is, and I think it is important, just my opinion, happy to be challenged on that. This might be the episode for you, though, because we do unpick that a little bit and put that into some context, I think, which is important. I don't think it's just black and white in terms of encouraging people to use correct vocabulary, or
well,
what
I remember
we might
you
decide as correct vocabulary.
Yeah, I do remember you mentioning. I think you've mentioned porridge words before when you did some reading on Kate's work before, John. So yeah, looking forward to that interview on Tuesday.
Yeah, it's great. It's very accessible, and Kate was lovely. So yeah, I'm looking forward to sharing that with everybody on Tuesday. And then Becky, we will be back next Friday. And excitingly, Becky, we're going to meet up, aren't we? Actually, in person.
In
More
real
than
life.
once in the next couple of weeks in real life, which
Yes, it's like
is bonkers.
buses.
Yeah, so I'm going to be down in your neck of the woods for a conference, and then looks like you will be up in kind of my neck of the woods as well. So look out for that. You'll see the two of us in the same room
In
at
the same
time.
place.
It's very exciting. Yeah, very exciting. We might even try and record a podcast somewhere.
That'd be good.
Know.
Yeah, let's squeeze one in.
Yeah, absolutely. In the meantime, we will leave you to it. Enjoy the rest of your half term if you're listening to it then. If not, I hope you had a good one, and we will see you on Tuesday.
Thanks for joining us. See you next time.